A very good day to start our Thermodynamic 1 presentation today. I wish you all days will be your nice days. Today, me with my teammates will discuss our presentation here with a system called Nozzle.
Hi everyone, I am Rendran from section 5 UTem. Today I am going to give an idea about what is a nozzle. So, what is a nozzle? Nozzle is a device which accelerates fluid. A nozzle is a tube with a distinct cross-sectional area used to direct the flow of the fluid. It is used commonly in controlling the speed, mass, direction, pressure, shape, and rate of flow. Generally, the velocity of the fluid increases in the nozzle on the loss of pressure. That's all from me. Thank you.
The first law of thermodynamics that related to a nozzle device. Nozzles are regarded as a steady flow engineering device. Mass balance for the nozzle is rate of mass in equal to rate of mass out because of conservation of mass. And so the conservation of mass is usually taken as density volume area in equal to density volume area out. For a nozzle, common assumption and ideation are no time for heat to transfer. This is because the fluid passes very rapidly through the process, so it does not have a chance to exchange a significant amount of heat with the surroundings. So Q dot is negligible. Moreover, nozzle don't have any mechanism to produce shaft work, so work dot is 0. Finally, nozzles are small devices, so even if they were oriented vertically, change in gravitational potential energy would be negligible. Since the Q dot equal to 0, W dot equal to 0, and the gravitational potential energy equal to 0, the energy balance for nozzle are rate of energy in equal to rate of energy out.
Now I will explain the second law of thermodynamics related to nozzle. Firstly, the second law of physics states that the sum of the entropy of an isolated system and its surrounding must always increase, which means that the entropy or the disorder of the universe is always increasing. The overall entropy will stay constant in ideal case wherever the system is in a steady state or is undergoing a process. Then, the direction of natural process is constant. It asserts the natural process runs only in one sense which is not reversible. Besides, entropy is a measure of how dispersed the energy of the system is amongst the way that system can contain energy. The second law of thermodynamics has several aspects that initially might be seen as different from those of conservation of mass and energy principle. Generally for nozzle, the energy balance reduced to 0 equals to H1 minus H2 plus V1 squared divided by 2 minus V2 squared divided by 2. Actually, there is two general equations for nozzle, which are actual nozzle and ideal nozzle. The equation for the actual nozzle will be H1 minus H2 equals to V2 squared divided by 2 minus V1 squared divided by 2. And the equation for the ideal nozzle, the only thing different between them is we add on a symbol of S as a precursor here. Hence, the second law of nozzle efficiency is we take the equation of actual nozzle divided to the equation of ideal nozzle. So the final second law nozzle efficiency will be bracket V2 squared divided by 2 bracket divide bracket V2 squared divided by 2 bracket S.
Hi guys, thank you for having me here today. I am Ichiwen. Now, let us take a look at example 1. Air at 450 kPa and 300 degrees Celsius enter an adiabatic nozzle steadily which has an inlet area of 100 cm² with a velocity of 50 meters per second and lifts at 175 kPa and 200 meters per second. We are asked to determine the mass flow rate passing through the nozzle, the temperature of the air at the exit, and the exit area of the nozzle. First of all, we have a nozzle, so draw a nozzle out as this will make us easily to visualize and write down all the unknowns and knowns. For example, P1 450 kPa, T1 300 degrees Celsius, V1 is equal to 50 meters per second at the inlet. And at the outlet, P2 is equal to 175 kPa, T2 we don't know, and V2 is equal to 200 meter per second. Since it is an adiabatic nozzle, so Q dot is equal to 0 and W dot is equal to 0, which means there's no heat flow and works in the system. Let's go through some assumptions that we can make. First of all, this is a steady flow process since there is no changing inside the nozzle with time. So basically means that the mass flow in has to be equal to the mass flow out. We can write down the equation as m dot 1 is equal to m dot 2 is equal to m dot. M dot refers to the mass flow rate. Secondly, we have air and we want to know whether it is an ideal gas or not. First of all, so we have to look at the critical temperature and critical pressure of the air and make comparison with the temperature and pressure given from the question. The critical temperature of air are 132.5 Kelvin and the critical pressure of air is 3.77 megapascal. And since the question have a high temperature, low pressure compared to the critical temperature and critical pressure of air, so we can assume that the air inside the nozzle is an ideal gas. The third assumption that we can make is the change in potential energy is equal to 0. Means there is no change in potential energy. Let we take a look at the properties. The gas constant R is 0.2870 kilopascal meter cube per kg Kelvin, and the specific heat constant that anticipated average temperature of 550 Kelvin is equal to 1.04 kilojoule per kg. That's all from me.
This is the solution for example 1. There is only one inlet and one outlet, so the mass flow rate and the inlet and outlet is the same. The specific volume and the mass flow rate can be determined by using the ideal gas relation, which is PV equals to RT. To calculate the V1, the specific volume, V1 is equal to RT1 over P1. R is the gas constant of A. The value is 0.2870 kilopascal meter cube per kg Kelvin. So by substituting all the value inside the equation, we can get a specific volume V1 equals to 0.3654 meter cube per kg. So we need to calculate the mass flow rate. The equation for mass flow rate is rho AV. So the area is given 0.01 meter square and the velocity at the inlet is 50 meter per second. So we calculate by substituting the V1 that we calculated before. So the mass flow rate at the inlet is 1.3684 kg per second. For B, we need to calculate the temperature of the air at the exit. Since we take nozzle as our system, the general energy balance for this steady flow system can be written as the heat flow rate minus the work equals to mass flow rate times the change of specific enthalpy at inlet and outlet plus the velocity at the outlet square minus the velocity at the inlet square divided by 2 plus the change of the potential energy. So from question and assumption, we know that the work and the heat and the change of potential energy is equal to 0. So we can simplify our equation. So we did not know the temperature T2. So we assuming average temperature at T1 is equal to 300 degrees Celsius. So by substituting all the value into the equation, we can get a T2 equals to 282 degrees Celsius. So for C, we need to calculate the exit area of the nozzle. Same with the method of question A, we need to calculate the specific volume for the V2. V2 is a specific volume V2 at the outlet. So by substituting all the value inside the equation, we can get a V2 is 0.9102 meter cube per kg. So since this is a steady flow process, so the mass flow rate at the inlet and the outlet is the same. So by comparing the two mass flow rate value and equation, we can get an area at the outlet is equals to 62.3 centimeter square. So we can get all the value and produce the TV diagram for example 1. So this is the TV diagram for example 1.
Example 2. Steam at 3 megapascal and 450 degrees Celsius enter a nozzle steadily with a velocity of 90 millimeter per second, and it leaves at 1 megapascal and 250 degrees Celsius. The inlet area of the nozzle is 50 cm square and heat is being lost at the rate of 70 kJ per second. Determine the mass flow rate of the steam, the steam velocity of the steam, and the exit area of the nozzle. Solution. First of all, we look at assumptions. This is a steady flow process since there is no change with time. Secondly, potential energy change are negligible. And lastly, there are no work interactions. Analysis. There's only one inlet and one outlet. Thus, mass flow rate inlet equals to mass flow rate outlet.
This is the solution for example 2. So we need to calculate the mass flow rate of the steam. So from the question we can get the pressure in the inlet is 3 megapascal and the temperature 1 is 450 degrees Celsius and the pressure 2 is equals to 1 megapascal and the temperature 2 is 250 degrees Celsius. So by referring to table S6, the superheated water table, we can get a V1 H1 and V2 H2, the value of V1 H1 and V2 H2. So by substituting all the value of V1 H1, we can get a mass flow rate at the inlet is equals to 4.171 kg per second. So B, we need to calculate the exit velocity of the steam. It takes nozzle as a system, which is control volume since mass cross the boundary. The energy balance for this steady flow system can be expressed in the red form as the E in minus E out equals to the change of E system equals to 0. So by substitute the exit velocity of the steam is determined to be by substituting all the value inside the formula of the heat flow rate minus the work equals to mass flow rate times the change of specific enthalpy and inlet and outlet plus the velocity at the outlet square minus the velocity at the inlet square divided by 2 plus the change of potential energy. So the question given give the heat loss is equals to 70 kJ per second. So by substituting the value inside the formula that I mentioned, we can get the velocity at the outlet is equals to 89.9 meter per second. So C, we need to calculate the exit area of the nozzle. So by using the mass flow rate equation, the mass flow rate equation is equals to rho A2 V2. So by substituting the value that given by the question, we can get the area at the outlet is equals to 107.99 centimeter square. So from the value that we calculate, we can conduct a TV diagram for example 2. So this is our presentation for this assignment, thermodynamic assignment. So thank you for listening. Thank you.